detail, and in this video we will be discussing about how to use this formula in a numericals. Charge will be under the equilibrium condition. On putting the magnitude part in the formula, what we will get, this is the to put the Coulomb's law. What is that? X by 2 and X by 2. We have to put the formulas over here. Plus X whole square. Now on cancelling the certain like terms, we will get the next step. The next step will be 8e, where e is equals to 1 upon 4 pi epsilon q by a square. So 8 into e we will get. We will start with the first formula, that is quantization of charge, which is Q equals to Ne. About this formula I have already explained in detail, and in this video we will be discussing about how to use this formula in a numericals. Second, we will be using the concept based on the Coulomb's law, that is Coulomb's law formula we will be using. What are the formulas we have learned in the previous topics? That is the formula of force between the 2 point charges present in vacuum, formula between the 2 point charges present in a certain medium, and the relative permittivity, that is epsilon r, which is equals to the ratio of the two permittivities, that is the permittivity in the intervening medium to the ratio of absolute permittivity in the free space. So now let's start with some of the questions that have been asked previously in the CBSE boards. The first question is, let us go for the first question. The question says, which is bigger, a coulomb or a charge on an electron? And how many electronic charges form 1 coulomb of a total charge? So the answer for this question will be the obvious, that 1 coulomb of charge is bigger than the charge on an electron. Let us see how is it. The charge on an electron, all of us know that the charge on an electron is E, that is equals to 1.6 into 10 to the power minus 19 coulomb. That is, it is having a charge of 10 to the power minus 19 coulomb. Now let's calculate the number of charges present in 1 coulomb of charge. So for that we have to use the formula N equals to QE, which is the based on the quantization of charges, that is N equals to Q by E. Here we have to put the magnitude. For Q we will be putting 1 coulomb. For E we have to put its magnitude, that is a numerical value 1.6 into 10 to the power minus 19. On solving this, we are going to get 6.25 into 10 to the power 18 electrons. So in 1 coulomb this many number of electrons are present, that is, and there we are having the one charge on an electron is this much of the coulomb. So naturally what we can say is that the number of electrons that are present in 1 coulomb of charge is 6.25 into 10 to the power 18 coulombs. So obviously 1 coulomb of charge is bigger than the charge on an electron. Next question, calculate the charge carried by 12.5 into 10 to the power 18 electrons. Mind it, here what are the parameters that have been given? We have to first concentrate on that. So first of all, here the number of electrons have already been given, that are 12.5 into 10 to the power 8, and we have been asked to calculate the charge carried by this much number of electrons. So which formula naturally we have to use? We have to use the quantization of charges, that is Q equals to N into E. Now the value of E is standard, which is 1.6 into 10 to the minus 19 coulomb. So in this formula, if you will put the value of N, which is 12.5 into 10 to the power 8, which is given, the standard value of E, which is by default, it is always 1.6 into 10 to the power minus 19 coulomb. On solving this, we are going to get the result Q equals to 2 into 10 to the power minus 10 coulomb. That means the charge carried by this much number of electrons will be 2 into 10 to the power minus 10 coulomb. This is how you will have to present your answer in the given format, so that there will not be any chance of losing. What is the next question? It says that the two identical charges capital Q each are placed at a distance of r from each other. A third charge small q is placed on the line joining the above two charges such that all the three charges are in equilibrium. This is our key point over here. Three charges have to be in equilibrium. So what will be the magnitude, sign and position of the charge small q? So first of all, we will depict the given situation in the form of a figure. We have to place the two identical charges capital Q and capital Q at the points A and C respectively, separated by a distance of r. Now where the third charge small q must be placed, the small q must be placed in between the line joining the two charges, then only the system of all the three charges will be in equilibrium. If you place them either to the right side or to the left side, all the three charges will never be in equilibrium. So in order to satisfy the given condition, if q is placed at a distance of x from A and B, then what condition we will be having? The charge will be, the small q will be in equilibrium if the forces exerted on it by the charges at A and C must be equal and opposite. Now when q is placed at a point B, now the charge which is at A, and the charge which is at C, they will exert equal and opposite force on the charge small q, then only the small q charge will be under the equilibrium condition. On putting the magnitude part in the formula, what we will get, this is the force between the charges at the point A and B, and this is the force which is present between the charges at point B and C. This is B and C. They are separated at a distance of r minus of x. Why? Because the total distances are, out of which the distance between A and B is x. So what will be the remaining distance? The remaining distance B and C will become r minus of x. So this is the two forces that are present on a small q charge because of the charge at A, and this is because of the charge at C. On cancelling the like terms, what we will get? This term, and on solving the term, we will get the position of a small q must be at r by 2. That is, small q must be placed at the center of the line joining the two charges. Now, the key point must be in order to find the sign of a small q. Now, how we can find the sign of a small q? The sign of a small q we can get by considering a concept that if capital Q is to be in equilibrium condition, if capital Q is in equilibrium condition, that means the two forces which are present on capital Q must cancel each other. Now, what is the force which is acting on the charge which is present at A? The C charge will be repelling this charge in this direction. The charge at C will be repelling the charge at A in this direction. So the charge at B, which is a small q, must attract the charge at A, so that the charge at A will become in equilibrium condition. So the charge at A is under the two forces. One is the attractive force by the small q, and one is the repulsive force exerted by capital Q. This is the key point. This is the key point or the deciding factor which will decide what should be the sign of small q. So the sign of small q has to be opposite to that of the capital Q. Then only the system of all the three charges will be in equilibrium. If you will take the sign of small q as same to that of capital Q, then the three charges will never be in equilibrium. Keep this key point in mind, that if the system of three charges are in equilibrium, the third charge has to be in opposite in nature. So now after that, our given condition will be force of repulsion between A and C must be equal to the force of attraction between A and B. So the repulsive force between A and C, that is repulsive force between capital Q, and the force of attraction by the small q must be same. That is, on putting the magnitude form, we can get this cancels out. So what we are left with, Q equals to Q by 4. So this is the magnitude part. What is the sign of the small q? Sign of this is just opposite here. Mind it, here we are not mentioning the sign of Q is positive or the sign of Q is negative. We are not mentioning any of the sign. We are just mentioning whatever be the supposed sign of the capital Q, the opposite sign must be carried by the small q. That should be your answer, not in a way that it should be positive or negative. This is the key point where you have to give the stress. The sign must be opposite to that of capital Q. Now, next question. Let's say another question which is again based on the condition of equilibrium. Now, 2-point charges of charge values capital Q and small q are placed at a distances of x and x by 2 respectively from a third charge of value 4q. All charges being in the same straight line. Now, calculate the magnitude nature of capital Q charge such that the net force experienced by the charge Q is 0. Here we have to take the two conditions. One is of capital Q charge and the other one is of the small q charge. Keep this in mind. In the previous question, we were having the equilibrium condition where all the three charges were in equilibrium. Here only small q charge is in equilibrium. So let us see first of all how the three charges can be placed. The three charges we are placing according to the figure. Here, from a charge 4q which is placed at A, the capital charge Q which is placed at B is at a distance of x, and the another charge small q which is placed at a distance of C at a distance of x by 2 from 4q. Now, what will be the key point over here in solving the question? For the equilibrium of the charge small q. Now, according to our question, small q charge is at equilibrium. Under which condition it will be equilibrium? When it is under the experience of two equal and opposite forces. Now, C will experience a force from A and C will experience a force from B. And these two forces must be equal and opposite. That is, FA and FB must be equal and opposite. So, what we can depict is that the charge on capital Q must be same as that on the charge of 4q. Then only the C will be under the action of two equal and opposite forces. So what will be the sign of capital Q? The sign of capital Q must be the same. Here again we are not mentioning that the sign should be the positive or sign should be the negative. Here we are just mentioning the sign of capital Q, which is at B, must be similar to the sign of 4Q, which is placed at A. So this one will be your key point. It is not opposite, otherwise the charge at C will not be in equilibrium. Now again, so according to our this key point condition, FA must be equals to FB. Now we have to put the Coulomb's law. What is that? X by 2 and X by 2. We have to put the formulas over here. So both of them are at a distances of X by 2 and X by 2. So like terms get cancelled out and we will get the magnitude of capital Q as equals to 4Q. So here again the concept we dealt with is the condition of finding the based on the equilibrium forces, based on which we have found the sign of the charge and the magnitude of the charge. Now any question which is based on such concept will be asked, you must be able to give the answer. Try to go for some more questions. In the coming slide I will give you some questions. Please try to solve it. Let's go for solving some questions previously asked in CBSE based on these topics. So here first numerical, let's see, the 2-point charges plus 1 microcoulomb and plus 4 microcoulomb are kept 30 centimeter apart. How far from plus 1 microcoulomb charge on the line joining the two charges will the net electric field be 0? How to depict the given situation in the form of a figure? Let's see, we have placed the one charge Q1 which is plus 1 microcoulomb at the point A, the other charge Q2 at the point B. These A and B are separated at a distance of 30 centimeter. Now let us suppose P be the point where the net electric field is 0. Now at the point P, we want to compute the directions of electric field E1 and E2 which are due to Q1 and Q2 respectively. Let us see first E1, it is due to the Q1. Now Q1 is positively charged, so at the point P, the electric field due to the Q1 will always be pointing away from the positive charge. That is, its direction will be this one. Similarly, if we go for the direction of E2, E2 is due to the plus 4 Q microcoulomb. Plus 4 microcoulomb, so it is due to again positive charge. So at the point P, the direction of E2 will be pointing away from the charge Q2. That is, E1 and E2 they are pointing in opposite direction at the point P. So diagrammatically we have shown them in the sense of direction. We have shown them E1 and E2. Now we can find the magnitude of E1 and E2. Further, let us suppose the point P is at a distance of x from the point A, and the remaining distance, that is the distance between P and Q2, will become 0.30 minus x, where we have converted it into meters. Now next, what we can have, the electric field at the point P will be 0 when we have E1 equals to E2 as they are pointing in opposite direction. Now the formula for E, already we know that it is KQ by R square. So if we will put this formula for our particular situation, what we will get? E1. Let us see E1 K, that is 1 upon 4 pi epsilon naught. E1 is due to the plus 1 microcoulomb. So here we have converted into coulomb as 10 to the power minus 6 coulomb upon R square, that is the separation between A and P is x. So we have taken x square. Similarly, if we want to find the value of E2, same magnitude. So 1 upon 4 pi epsilon naught. Here E2 is due to the plus 4 microcoulomb. So we have converted it as 4 into 10 to the power minus 6 coulomb upon the separation between P and Q2. It is 0.30 minus x whole square. Now on cancelling the certain like terms, we will get the next step. The next step will be this step, and on solving this, we will get this value. If we will solve this equation, what we will get? X equals to 0.10 meter, that is 10 centimeter to the right of plus 1 microcoulomb charge. That means from the point A, if we have the 10 centimeter of distance, there the net electric field will become equals to the 0. This is how you can solve the numericals based on electric field. Now next, go for the next numerical. The 2-point charges plus 16 microcoulomb and minus 9 microcoulomb are placed 8 centimeter apart in air. Determine the position at which resultant electric field is 0. That means how to depict it? If we place 16 plus 16 microcoulomb at the point A, this is Q1. Q2, which is minus 9 microcoulomb at the point B. The A and B, they are separated at a distance of 8 centimeter in air, and P is the point where the net electric field we want to compute to be the 0. Now our first target should be to find the direction of E1 and E2. Now since E1 is due to Q1 charge which is positive, so always in this direction it will be pointing away from the positive charge. So at the point P, this is the direction of E1. Now E2 is the electric field due to the Q2 which is negative charge, so its direction will be always towards the negative charge. So that is why at the point P, the direction of E2 is towards Q2. Direction of E1 is away from Q1. Keep this in mind. And now these E1 and E2, they are pointing in the same direction. Now further, let us assume that the point P is at a distance of x centimeter from the point A. So the remaining distance between P and Q2 will become 8 minus of x. Now we want to find it magnitude wise. What we can have, if P is the point where the net field is 0, so what we can have at the point P, we have E1 plus E2 equals to the 0. Why? Because E1 and E2, they are pointing in the same direction. So when they will add up, then only they will give us the net electric field as 0. Now again, the magnitude of E is equals to KQ by R square. So on putting the magnitudes, K is there. Now this E1 is due to Q1, which is plus 16 microcoulomb. So here we have converted into coulomb as 10 to the power minus 6 upon separation is x minus 10 to the power minus 2. Why we have included? Because we have converted centimeter into meter. Similarly, E2 is due to minus 9 microcoulomb. So here we have converted it as minus 9 into 10 to the power 6 coulomb, and the separation is 8 minus x, and we have converted into meters, and this is whole square equals to 0. On solving this and cancelling the like terms, we will get this step. Further, if we will cancel the steps, we will get this equation, and now the value of x comes out to be the 32 by 7 or 32 centimeter. Two values we will get for x, because we are having plus minus sign. Now, if we see the situation x equals to 32.7, that means x comes out to be the somewhere between 4 point something value. That means it lies between A to B. Now, in between A to B, what we are finding, if we have a point P where electric field is to be the 0, it can never be 0. Why? Because E1 and E2 in between A and B will always be pointing in the same direction. So, this particular situation we have to neglect, where the net electric field can never become 0 in between A and B. Now, next, how can we find the other point? Now, the remaining point is x equals to 32 centimeter from A. That means if we move from A towards 32 centimeter, that is towards the right of Q2. That means in this somewhere over here, towards the right of Q2, there E1 and E2 will be pointing with there. See here, E1 will be pointing in this direction towards the right, and E2 will be pointing opposite to E1. So this is the point P where E1 and E2 can cancel each other, and the net electric field will be the 0. So mind it, when we are having the two unlike charges, that is one is positive and negative, so the net electric field will be 0 always on the other side of the charge. That is, it will never be in between the two charges. So at x equals to 32 centimeter, the electric field will always be the 0. This key point you have to keep always in mind. In between A and B, the net electric field can never be 0. Next, go for the next question. Now we have 2 point charges plus 6q and minus 8q are placed at the vertices B and C of an equilateral triangle ABC of side A. Obtain the expression for the magnitude resultant electric field at the vertex A due to these two charges. So this is the given figure. ABC is an equilateral triangle where at the point B we have placed a plus 6q charge, and at the point C we have placed minus 8q charge. Now our aim, this equilateral triangle is of side each of side A. Now our aim is to find the net electric field at the vertex A. So how we can find it out? Now at the vertex A, this plus q charge will be exerting a force or the electric field in this direction because it is positive. So this is EBA. It is denoted by EBA, electric field pointing from B to A, which will be pointing away from the plus q charge. Now next we want to find the electric field due to this negative charge which is at the C. So negative charge at the point A will take the electric field towards itself. So electric field at the point A will be pointing towards the negative charge. So this is the direction EAC, that is electric field pointing from A to C, it will be in this direction. Now diagrammatically or direction wise we have represented the electric field B and electric field C. Now what will be the resultant electric field at the point B? It will be the vector addition of EBA and EAC. Now let us see what will be the vector addition. How we can compute? Here the magnitudes of EBA. Now the general formula for electric field is KQ by R square again. So here this EBA, it is due to the plus Q charge. So here we have to put Q as 6Q, and the separation between the A and B is A. So that is A square, that comes out to be the 6E. Now here for simplicity we have substituted E as a general formula 1 upon 4 pi epsilon Q by A square. So this Q by A square complete part we have substituted as E. So our EBA becomes 6 of E. Next we want to find EAC. Now what is EAC? EAC is due to the minus 8q charge. So here we have to put the magnitude of 8q upon A square, that comes out to be the 8E, where E is equals to 1 upon 4 pi epsilon Q by A square. So 8 into E we will get EAC. Here we are not putting the magnitude that is negative charge, here only we are keeping the magnitude part. Now let us see what will be the net electric field. The net electric field at this point will be always equals to the Here the net electric field is the vectorially we have to add. So what will be the vector addition of EBA and EAC? It will be the under root of EBA square plus EAC square plus twice of EAB EAC cos 120 degree. Now let us put the value 6E, 8E and cos 120 degree is minus 1 by 2. On solving this value, we will get the formula for E net as equals to the E net equals to the E root 52. And now we will put the value of E as 1 upon 4 pi epsilon naught Q by A square. So this complete part becomes the magnitude of net electric field at the vertex A of an equilateral triangle. So here certain key points that you have to keep in mind is that vectorially you have to add these two electric fields because this is a vector quantity and the angle between them matters a lot. So we have to put the value. Next, go for the other question. Four charges plus Q, minus Q and minus Q are placed respectively at the four corners A, B, C and D of a square of side A. This time it is a question based on a square. Calculate the electric field at the center of the square. Now let us see how we can depict the given situation. Here A, B, C, D are placed at the corners of a square. Now plus Q and plus Q are placed at A and B respectively. Similarly, minus Q and minus Q are placed at D and C respectively. I think this will be clear to you. Now, at O is the center of this square where we want to compute the net electric field. Now, let us see step by step. First of all, we will take the plus Q charge at the point A will exert an electric field in this direction. Why? Because it is a positive charge. The electric field will be pointing away from the plus Q charge. So, this is the direction of EA. Keep this in mind. Similarly, the charge plus Q which is placed at B will exert an electric field EB. Again, it will be away from the, it will be pointing away from the plus Q. So, at the point O, we have to draw this. This is the direction of EB. Next, C. The direction due to EC, that is direction due to C minus Q charge. Now, at C, minus Q charge is placed. So, the electric field due to a negative charge always points towards the negative charge. So, this is the direction of EC. From O, EC will be pointing towards the negative charge. Keep this in mind. Similarly, at the point D, we have placed a negative charge. Again, ED, the electric field which is due to negative charge will be pointing towards the point D, that is towards the negative charge. So, this is the direction of ED. I hope now the direction will become clear to all of you. Once again, I will show it to you. EA is in this direction away from plus Q because it is due to positive charge. Similarly, EB is pointing away from the plus Q because again it is due to positive charge. EC is towards the negative charge. It is in this direction. Similarly, ED is also towards the negative charge. So, these four directions you have to keep in mind. Rest magnitude wise, we can find the value of the electric field since all the charges are of equal magnitude. Here, the charges are of equal magnitude Q, Q, Q and they are at the same distance R from the center. Now, see here, the distance of O with respect to A, with respect to B or with respect to C or with respect to D, it is equal, which is equals to R. So, this R distance we have to compute. Now, here it is already given that the side of a square is A and here the side of the square is A. So, how we can find the value of this R? This R we can compute it in the form of using the right angle triangle. Here if we are having a right angle triangle like this much, if they are at right angle, this is R and this is A. So, what we can have, the magnitude of EA, EB and EC each will be equal and that is equals to KQ by R square. Now, the value of R using hypotenuse theorem, we can get it as A by root 2. So, now we will put the magnitude as KQ upon A by root 2 whole square. So, that becomes 2 into KQ by A square. This is the magnitude of every magnetic field, that is EA, EB, EC and ED. The direction I have mentioned in the figure. Now, let us see E1. Now, we want to find the value of E1. Let me clear the figure first. Now, E1. Now, first we will find E1, which is the EA plus EC that is pointing in the same direction. So, EA and EC, they are pointing in the same direction. So, we will be having E1 is the net electric field. So, magnitude wise, we have to simply add up these values. That is, EA is 2 into KQ by A square. Similarly, 2 into KQ by A square. So, on adding, we will get 4 KQ by A square. Now, next, what we will be having? E2. What is E2? E2 is pointing in this direction. EB and ED, they are pointing. So, we have to add these two electric fields. That is why we will get E2, which is EB plus ED. Again, on the following the same line on the previous step, we will get E2 as 4 KQ by A square. So, what is E1? E1 is the net of EA and EC. Similarly, E2 is the net of EB and ED. Next, we want the net electric field. So, the net electric field will be equals to the under root of E1 square plus E2 square. So now the sum of this and this will give you the net electric field. So magnitude wise we have to add up this value and this value. Ultimately it comes out to be, on solving this square or square root, we will get 4 into root 2 k cube by a square.